welcome back to Manish Kumar channel. Today we are going to discuss about the exponential forms. So for a given complex number z, which is expressed as x plus iy, we can write this z as an exponential form using argument and modulus. So r is equal to modulus of z and theta equal to argument of z. Now you can see in the plane x plus iy can be expressed as exponential form. Okay, so theta is a counterclockwise rotation. Now let us see example. Find the exponential form of z equal to 1 plus I. Already r can be calculated using the formula. So r is going to be root 2 and theta equal to tan inverse 1 by 1, which is going to be pi by 4. Now this point lies in first coordinate, right? So we do not require any correction, right, in argument value. So we can directly write z as root 2 e power I pi by 4, right? Now let us see another example, example 2. So convert z minus 1 plus iota root 3 to exponential form. So in that case, r using the same formula, we got r as 2 and theta equal to tan inverse root 3 by minus 1, which is going to be minus tan inverse root 3, and which is come out to be minus pi by 3. So here, since theta lies in the second quadrant, right? So we need correction to add pi, right? So once you add the pi, then your z is converted into the exponential form 2 times e power I 2 pi by 3. So this is very important. I request all of you to follow my previous video on arguments, then you will understand why we are adding pi here, okay, to get the correct range of principal argument. Now we'll see the products and powers in exponential form. So if you see, we have z1 and z2 be two complex numbers. Then what about the product z1 into z2? z1 into z2 can be written as r1 into r2 e power I theta 1 plus theta 2. In general, r e power I theta to the power n can be written as r to the power n and e power I n theta. So for example, if we have z1 as 3 plus I, right, this point, and z2 is 1 plus 2i, and with the angle theta 1 and then angle theta 2 respectively, then if you do product these 2 points, so you will get this in the form of addition. What will happen? Theta 1 plus theta 2 will be the total sum of the angle, right? Total sum of the angle theta 1 plus theta 2, and then you can use this formula to verify, right, in exponential form. As you know, very famous Euler's formula. So Euler formula is e power I theta cosine theta plus I sine theta. And there are useful identities, e power I pi equal to minus 1 and so on, right? So this is a fundamental in expressing complex number in terms of trigonometric functions, right? So let us see one example. Express e power I pi in terms of real and imaginary components. So you can write it e power I pi from here. You see from the formula cosine pi plus I sine pi, which is equal to minus 1 and 0 times of I, which is going to be minus 1, right? And another famous formula, De Moivre's theorem, for any uh, exponential form of a complex number r e power I theta to the power n can be written as using Euler formula. You can write this and power n, and then De Moivre's theorem says cosine n theta plus sine n theta, right? So let us see one example. Compute cosine 3 theta plus I sine 3 theta using De Moivre's theorem. So now solution is cosine 3 theta plus I sine 3 theta can be written as cosine theta plus I sine theta to the power 3, right? Let us talk about the arguments of products and quotients. So if Z1 and Z2 be two complex numbers, then the following identities are going to be true. So argument of the product is equal to the sum of the arguments, right? And you know the quotients argument Z1 by Z2 is nothing but argument of Z1 minus argument of Z2, right? So already we have seen that the product of complex numbers z1 z2 equal to r1 r2 e power I theta 1 plus theta 2. z1 by z2 is equal to r1 by r2 e power iota theta 1 minus theta 2 provided z2 not 0, right? Then in that case, let us consider one problem. Given z is 4 e power I pi by 3 and z2 equal to 2 e power I pi by 6, find z1 by z2. So using the above formula, z1 by z2 equal to 2 e power I pi by 6, right? Difference angle. Now let us talk about one more important identity. Is this product argument is true for principal argument as well? So not in general. The answer is this is not always true due to the range restriction of principal argument. So principal argument of z1 plus z2 is not necessarily equal to the principal argument of z1 plus principal argument of z2. But if you see a simple argument, right? Argument of z1 into z2 equal to argument of z1 plus argument of z2, which is always valid, right? But if we replace by principal argument, right, then this is not always true. So this is where we can see few examples. So let us take if z1 equal to minus 1 and z2 equal to minus 1. Then calculate argument of z1 is pi. Argument of z2 is again pi. This is principal argument, right? And the product of z1 z2 is going to be 1, for which principal argument is going to be 0, right? And the sum of the argument right hand side is going to be pi plus pi, which is 2 pi, which is no longer belonging in this principal argument range, right? So we adjust by subtracting 2 pi, right, to the corrected value. So 0 is not equal to 2 pi in general, right? Hence additivity fails. You got it. Similarly, if you see z1 equal to minus 1 and z2 equal to I, then the same case 3 pi by 2 does not belongs to the principal argument, and then this additivity fails, right? So we need to subtract 2 pi to adjust this identity to be true, right? So conclusion, so additive property of principal argument fails, right, when argument of z1 plus argument of z2 falls outside of this interval, right? So adjustment modulo 2 pi is needed to bring back it within range, right? But if real part of z1 is greater than 0 and real part of z2, right, is greater than 0, right, then in that case principal argument additivity holds true. So this is the condition. If you see the two examples which we have taken, in all the cases real parts are not greater than 0. So real part of z1 is less than 0 actually, right? So if we have this condition, real part of z1 greater than 0 and real part of z2 greater than 0, then this additivity property of principal argument holds true, right? So thank you very much. Thanks a lot.